Okay, welcome to Let's Get to the Marks. I'm going through the Physics and Maths Tutor pack for Aromatic Chemistry for A Level Chemistry AQA. It's a revision pack you can find on the awesome Physics and Maths Tutor website. Let's get into it. Paracetamol is a medicine commonly used to relieve mild pain. Traditionally, paracetamol has been made industrially in a three-step synthesis from phenol. So here we have a reaction synthesis where we can see phenol was step one, and then it's changing with each step of this three-step reaction. We can see nitrate group added, then an amine group, and finally we've got like a carbonyl group added. So name the mechanism for the reaction in step one between phenol and 4-nitrophenol. So in order to understand this, let's look at what's taken place between phenol becoming 4-nitrophenol. So what have we added? We've added NO2, and you need to know this off by heart. It's one of your key bits of content. What happens is the nitronium ion, which is a cation, it's got a positive charge. This is an electrophile because of its positive charge. It seeks out electron-rich areas, and the electron-rich area in a benzene ring is the delocalized ring. So a pair of electrons break out of the delocalized ring and go towards this cation here. And then what we have is a horseshoe forming. Remember, these points on the benzene have hydrogen attached, so the NO2 group attaches where one of the hydrogens attaches. In order to restabilize the ring, the bond with the hydrogen breaks, and the pair of electrons from that hydrogen bond go back into the ring, reform the delocalized ring. So this is basically a substitution reaction, and we start with an electrophile because the NO2 plus is positive and seeks out electron-rich areas. So we're looking at electrophilic substitution. Okay, as I work through this physics and maths tutor pack, this is only part one of three. This is the first video of three. I suggest at the start of each part to a question, i.e. question 1, A, B, C, D, E, F, G, at the start of each one, you pause the video, read through the question, and then have a go yourself on a scrap bit of paper, which you can throw away afterwards. Then you unpause and watch the walkthrough. Now, I'm only covering one question in this aromatics pack, but I'll be covering the rest of it in two more videos. Okay, so in this part B, we need to complete the equation for the reaction in step 2. And you've got 4-nitrophenol here at the start. So the nitro group's not as high priority as the hydroxy, so it's called 4-nitrophenol. And then it forms 4-aminophenol. Again, the amino group's not as high priority as the hydroxy. And what happening is this oxygen is being swapped here, this O2, for these two hydrogens here on the amine group in the product. Look, we've gone from an NO2 group to an NH2 group. So we could ask yourself, what's been added? Fairly obvious here. What's happened is we've got a bit of substitution going on, and we've got some hydrogen being added in the place of the oxygen. So it's like a reduction when you add hydrogen. It's a reduction reaction. We've reduced this with hydrogen. How many oxygens are we removing, and what happens to those oxygens? What do they form? Well, remember, we've probably got an excess of hydrogen in this reaction. You can do this with hydrochloric acid and tin, or you can do this with hydrogen and a nickel or palladium catalyst for reduction of nitrobenzene. And essentially, because there's two oxygens, I'm going to need to make 2 molecules of water. And that's going to require, in order for me to use up the 2 oxygens on the nitro to remove them, I have to form 2 molecules of water, which means I need 2 H2O, which means I need 2 H2. I need 2 lots of hydrogen. Even though at first it appears only 2 H's have been added, 2 of the H's go on with the oxygen to combine to form a water molecule. So actually you need 4 H's, even though it appears like only 2 H's are added. Now this reaction normally requires a catalyst. It's not part of this question. You can use hydrogen, as I said, with platinum, palladium, or nickel catalyst. You can use hydrochloric acid and tin, so which is a common one in AQA, they like you to say. So there's lots of different ways you can reduce um, this nitrobenzene to a phenylamine. So let's look at part C. In theory, either ethanoyl chloride or ethanoic anhydride could be used in step 3. Complete the mechanism for the reaction of 4-aminophenol with ethanoyl chloride. RNH2 is used to represent 4-aminophenol in this mechanism. So the R group here is actually the product of step 2. I've done the old again. So what we want to do is we want to draw a hydroxy group because it's 4-amino phenol hydroxy being more important. And then, so you always name the hydroxy after the amine group there. So then we got the amine group at the bottom. Now that is going to be represented in this by this R over here. So we're just writing R with the NH2. So the R really represents the benzene with the hydroxy on it. You can see here the lone pair from the nitrogen is attacking that carbon because that's delta positive due to the polarized bond of the C-O-O bond. The oxygen, they're showing a curly arrow going from the double bond to the O. You should know what that represents. That means we're going to end up with a lone pair because each arrow is worth 2 electrons. So we're going to end up with a lone pair on the oxygen and a negative charge. We've got the methyl group, and then we've got the chlorine atom coming off. And of course, we've now attached nitrogen and 2 hydrogen atoms. And we've got the R group. Now, here's our first problem. Nitrogen isn't supposed to have 4 bonds. It normally has 3 bonds coming off it. What happens to a nitrogen when you have 4 bonds around it? Think of the ammonium ion. What charge does nitrogen get? You should realize that the nitrogen atom will now have a positive charge on it because it has 4 bonds. So we always count the bonds around a nitrogen atom when we're doing mechanisms. And if there's 4 bonds around the nitrogen, we want to put a positive charge. Okay, so it's like a nitronium ion or whatever it is. But it has a positive charge. Now we look up here, the oxygen is going to donate its pair of electrons back. So whenever you see the oxygen like this, when temporarily that carbonyl bond has been broken, it's going to reform. And that would mean that carbon would have 5 bonds around it, and carbon can't have 5. So the chlorine's got to be sent off. So our chlorine's going to break off. The carbonyl bond that was temporarily destabilized will reform. And then over here, one of these hydrogens, I'm not going to do this one because it looks a bit confusing. I'll do this one down here. One of these hydrogens its bond is going to break, and the pair of electrons from the bond are going to go to that positive nitrogen and stabilize the molecule by donating their electrons to the nitrogen. And that's going to leave us with a hydrogen ion coming off the side here. And of course, you've got a chlorine ion coming off the side here. Now, again, the product is not part of the marks. That's not what they want here. They want the mechanism. So they're looking for curly arrows and lone pairs and charges. So those 3 curly arrows, the plus and the lone pair with the minus on the oxygen, that's going to get you your 3 marks, or your 2 marks in this case. A lot of work for 2 marks. This is the product, what you'd end up with, which I've drawn here. But you'd also get a chloride ion released where the chlorine bond is broken. Where one of the hydrogens breaks to stabilize that positive nitrogen, you're going to get a hydrogen ion, and you guys can guess what the product is going to be, the side product. It's going to be HCl. Now, this is not part of this question. The part of the question is that first bit I've drawn there with the 3 curly arrows, the plus, the minus, and the lone pair, and that will get you the 2 marks. Okay. It is important to know that you form hydrogen chloride as a side product and to be able to work out what your side products are, as we'll see in the next part of the question. Let's move on. Keep moving on, keep moving on, keep moving on, keep moving on. In practice, ethanoic anhydride is used in the industrial synthesis rather than ethanoyl chloride. Give one reason why ethanol chloride is not used in the industrial synthesis. Pause the video, see if you can have a go, and then unpause and watch the walkthrough to the answer. Okay, let's do it. So, looking green here with the ethanoic anhydride. The green bit of the ethanoic anhydride, what do you think that's going to go on to form when it combines with a hydrogen ion? Now look at the ethanoyl chloride and the bit that I've highlighted in green. That's the bit that's going to break off in the mechanism and join with the hydrogen ion that also breaks off. So what's the difference in the side products that they're going to form? And that's going to give you the answer to the question. So let's take a look back at the original reaction mechanism for the question before, and then we're going to be able to work this out. So this is the reaction mechanism from the question before. If I zing this down into place, I put this up for the last question, how we worked out the mechanism. But look what happens. The chlorine atom breaks off. When you've got ethanoyl chloride, the CH3, C double bond O, and the chlorine atom, look, the chlorine atom is going to snap off. Remember that one of our H's comes off in the middle part of that mechanism as well to neutralize that positive carbon atom. And so that's going to form hydrogen chloride. However, if it was acid anhydride, um, what would happen instead is, instead of a chlorine coming off, the bit I highlighted in green earlier was a carboxylate group. And that carboxylate ion that comes off instead will combine with the hydrogen from the nitrogen to make like ethanoic acid, which is vinegar, essentially. And so what's the difference in danger between hydrogen chloride and vinegar? What's the difference, and why might people prefer to use the acid anhydride and get the ethanoic acid side product than hydrogen chloride? And that will get you your answer if you can work that out. So of course the CH3COO with a minus charge, or carboxylate ion, breaks off, joins with the hydrogen ion, and you get CH3COOH, and of course that's the formula for ethanoic acid. So the acid anhydride tends to be a safer reaction than using ethanoyl chloride. So in practice, give a reason that we use ethanol chloride in industrial synthesis, and it's because it forms ethanoic acid instead of hydrochloric acid. Or HCl fumes, hydrogen chloride, which is a gas, sorry, not an acid. But hydrogen chloride fumes, HCl, are corrosive, whereas ethanoic acid is not corrosive. Okay, cool. That was a bit of a long waffle for a 1-mark question, but I hope it helps. And if you're liking the video, make sure you hit the like, subscribe to the channel, and share. Leave a comment. It encourages me to make more of these videos to help you get through your A-level chemistry. Okay, let's get to the next question. In step 3, other aromatic products are formed as well as paracetamol. Draw the structure of one of these other aromatic products. So we're going to need to go back and look at what's happening in step 3, because there's some other products that aren't shown in this mechanism that are formed. So let's go back and have a look. So if we zing back up here and we look at step 3, what it's shown us is that we've ended up with our CH3CO taking the place of one of the hydrogens on the amine part of this compound. Instead, we can have the oxygen on the hydroxy group attack that delta positive carbon. And we're not going to go through the whole mechanism, but a simplified version of it is that the oxygen lone pair that's on the hydroxy group attacks that carbon atom on the polar carbonyl bond, and we get the carbonyl bond attaching there, essentially. So this is a bit oversimplified because you'd have the chlorine attached, etc. There'd be the chlorine would be breaking off and the hydrogen would be breaking off to form a hydrogen chloride side product, the same. But essentially I'm just trying to show you here that it could attach there to that oxygen, and we could kind of get like an ester link formed at the top here with an O to a C double O with a methyl attached. So that's our other option there that can be formed as a side product instead. And I'll draw the structure of that out here so you can see that. And there you go. Only 2 more parts to do for this question. That structure there that I've circled is the answer. It's just kind of showing you a bit of working beforehand, even though it wasn't fully correct. Let's move on to the next bit. So we're looking at F here. Chemists have recently developed a 2-step process to produce paracetamol from phenol. In the first step, phenol is oxidized to hydroquinone. As we can see there, we've got a phenol group, we've got hydrogen peroxide attacking it, and then we've got like well, I can't even say that. What is it? Hydroquinone, where you've got a hydroxy group, 2 opposite each other across the benzene, and water formed. In the second step, hydroquinone reacts with ammonium ethanoate to form paracetamol. Complete the equation. So do you know the formula for ammonium ethanoate? Think about it. Ethanoate, it's a carboxylate ion. It's CH3COO with a minus. It's a carboxylic acid where the hydrogen's been removed, and it's been replaced with another positive ion instead of a hydrogen ion, and this time it's the ammonium ion. You should know the formula from GCSE. It's NH4+. So that's our formula for ammonium ethanoate. So let's have a look here at what's different in the reactants to the products. And what you should find is that if you look at the carboxylate group, the CH3COO, we've only got one O. There's only one O now, so it's lost an oxygen. Also, look where the hydroxy group was. That's lost an oxygen too. And we've lost 4 hydrogens, 3 from the NH, and it could be the H from the hydroxy's gone as well. But a total of 4 hydrogens and 2 oxygens have come off, and that means we need 2 water molecules to balance it all up. Okay, we're coming to the last part of the walkthrough here. So don't forget to smash the like, subscribe, and let's get into the final bit of the walkthrough. So let's calculate the mass in kilograms of hydroquinone MR110 needed to produce 250 kilograms of paracetamol. So what we need to do here is we've got a mass and we've been given MR. This should strike clues in your brain. What's the equation? It's going to be mass over MR times moles. Let's just draw out the structure of the hydroquinone. So we know that it's got 2 hydroxy groups and it has an MR of 110. We don't know the mass of hydroxyquinone, just checking out the formula for the paracetamol now. So now I can draw out the paracetamol. Just had to have a sneaky look back there because I can't remember this off by heart. Got a hydroxy group down up there, up the top, and then down the bottom, another quick double check, NH. Okay, NH. We had CH3 coming off and then a carbonyl bond. Awesome. We need our mass over MR times moles. Let's get into it. It's a 1-to-1 reaction. It shows us that in the step. So we need that for coefficients. When you're finding out the mass of something and you've got the mole and you can work out the moles of something else, then you know that once you worked out the moles of one, you worked out the moles of the other. So my first thing is I've been given I need to find out. I've been given 250 kg of paracetamol. So from the formula, I can work out its MR. I think it's got 8 carbons there. Notice I've drawn the hydrogens on to make it easy for me to add up. It's got 9 hydrogens, 1 nitrogen atom, and 2 oxygens. So if I add that all up, 8 times 12 is 96. I've got 9 ones for the hydrogen, 14 for the nitrogen, 32 for the oxygen. Smash that all in the calculator. And that equals 151, and that's our MR of paracetamol. We know we got 250 grams, times that by 1,000 because we use grams in amount of substance in chemistry. We don't use kilograms. So we want 250,000 grams, which is our mass, divided by the MR of 151, and we get 1,655.6 moles. Now, I'm going to times that by 110, but let's just explain why. So that's my moles of paracetamol. Remember I said it's a 1-to-1 ratio. If I know that I have 1,655.6 moles of paracetamol, as it's a 1-to-1 ratio, I know I've got the same moles of hydroquinone. Now, luckily they've given us the MR of hydroquinone. They don't want us to do that same thing twice where we have to calculate the MR. So we're just going to do 110 times the 1,655. God, I lost my train of thought there, 0.6 moles. So we're going to multiply those together. And what we're going to get when we do that is 182,116 grams. But don't forget, we need to convert that to kilograms. So take that answer from your calculator and divide by 1,000, and you'll convert that into kilograms. And that's going to end up being 182.116 kg. Now we can round in A-level chemistry to 3 sig figures, so we can just call it 182 kilograms. And there you go. That's your answers for 3 marks. Now, guys, sharing's caring. Punch up the like, subscribe. Let's get to the marks.
You're still here? It's over.